Alright, hey and welcome to example 9. In this one we're going to take a look at a more less basic example of spring constraint, and we're also going to do a little comparison between spring and glue and see what the difference is and like kind of how to use them differently and stuff like this. First of all, we're just going to go ahead and with our simple usual setup on a box here. We're going to use a box, volume, some points, Warner fracture of that. We're gonna create the constraints. However we want. This time I'm actually gonna use adjacent pieces from points because I find that works a little bit better with spring. So put the connection type to adjacent pieces from points. Then create the usual constraint name, constraint type, put the string to spring. So our data name is going to be spring. Then pack the points. Pack the points or pack the pieces. We're going to group everything that is inside of this box. We're going to group. We're going to set that to inactive with this wrangle. Exactly the same we did before. When we create an active attribute, we put it into 1. So all pieces are initialized as active. Then we're going to put if the pieces inside of this group called inactive, they're gonna be put to active equals to 0, which means that these bottom ones is gonna be 0, which means that this whole thing will be stable and in place. So we're also gonna create a sphere here, just simple sphere. Just move it up a little bit to use as an RBD object that's gonna crush into this pillar here. And that's all. We've put all the nulls here to kind of find the pieces or the primitives later on in the .NET, and we're gonna go into the .NET. So let's have a look. In the .NET we have the RB packed object, which is the tower. We have the RBD object, which is the ball. We're gonna put some initial velocity on the ball, minus 17, which means that it's gonna go minus 17 in the x-axis. We're gonna merge those two. We're gonna pipe that into a bullet solver. And it's gonna look like this in the bullet solver. And then we're gonna add a constraint network. We're gonna find our constraints here. We're gonna do a little bit interesting thing here, but first of all, we're gonna add both a glue constraint relationship and a spring constraint relationship. We're gonna put them into a switch. The switch is gonna go into the second input, and the switch is gonna be put to 1. Because we want to access input 1 of the switch, which is the spring constraint here. In the spring constraint, we're going to put the strength up a little bit. We're going to put the damping way down to get a really slow dampening of the springs, which is going to make a really cool result. We're going to put data name to spring. That's all we need to do in spring. In the glue constraint relationship, we're going to put the strength to 1000. That's all up here. And the data name to spring, because we want both of these to have the same data name. Once we switch over here, the glue is still going to use the same primitives and points to create its network. So the spring doesn't really define what kind of type of constraint it is. It's just a way to separate it out, to kind of say that this constraint network is going to be used here, this constraint is going to be used here. So if you have multiple constraint networks, the data name is going to be important. But if you only have one and you only focus on one, you can have the data name to just spring, and you can put it to both of these. So the switch, put it to 1 because we want to access the spring constraint here. You can see that this is dotted and this is full, so therefore we access this one. That goes into the second input of the constraint network. Then we add a ground plane like this, merge that in, and a gravity, and that is it. So now if we go ahead and hide this, and instead we're gonna show the guides, we can see that we have multiple of these springs here on the geometry, and it's quite slow. This is quite heavy because the spring constraints are a quite heavy constraint, which takes longer to simulate. We're gonna show the geometry, we're gonna hide the spring constraints, and we simply gonna simulate and see what this looks like. So now we have spring on these pieces, and we can see they bend, they whip, they do a lot of crazy things here, and the ball falls back, and the springs are kind of correcting themselves. And they are going on to the other side, and yeah. It's gonna keep on pendling here for a little bit, but as you can see, it's a really cool result when this impacts. It's like a rubber almost. I don't know. But as you can notice, spring constraint they don't break naturally. They don't have a breaking point, which is really interesting. And if we instead go ahead and switch this over to glue, we put it to 0. So the input 0 and the glue constraint is being accessed. If we now simulate this, it's gonna break because glue constraints break naturally. And it's very fast and very like simple. No bending or anything. So what if we wanted to use the springs, but we did want to break them? We want to use some kind of attribute to break these. So a spring is actually it kind of bends, right? So we could imagine they get an angle, and they actually get an attribute called angle. So once a spring bends, the angle increases. Let's simulate a little bit and see what our angle attribute says. So let's check this moment right here. We can see a pretty big bend here in a lot of pieces, but these are still straight compared to each other. All right. Let's check the geometry spreadsheet. Let's go to the RBD packed object, geometry, and let's click that. Let's filter out, hide all attributes, and let's find the. Let's see. Do we have an angle? Huh. Aha, we're right. We need to actually go to the relationships. Here we go. We need to go to the constraint network. We need to find. Let's see. What do we need to find? We need to find the geometry. Here we go. And in the primitive here, we can hide all of them. See, relationships is referring to the constraint network. The constraint network and the constraint network again and the geometry on top of that. So now we're accessing the point and the primitives. So if we go ahead and we can see angles here. We can see there's an angle. Not all of them are angled that much. But you can see some of them are even angled 0.3 radians, which is a lot. That's like, isn't 0.5 radians 90 degrees? I think. 1 radian is 180 degrees, I think, something like that. Regardless, it's getting up closer to 90 degrees of our angle. So that means that maybe we can go ahead and break these bonds based on the angle of the constraints. So if a constraint gets over a certain angle, they are removed. And again, we can do this with a subsolver. So let's say we have a subsolver here. Let's connect that to the third input of the constraint network. All right. Let's go ahead and dive into this. Let's enable it. Let's dive in. Let's say we want to access the relationship geometry. Relationship geometry, as you remember, we have 4 nodes. This is one of them. Now we're accessing what comes into the constraint network. Let's say we want to delete any constraint, any primitive that has an angle greater than 0.1. Okay, so they can still bend a little bit, but once they bend above 0.1, they will break, they will be removed, and the pieces will fracture. You know, we can do that by writing some vex here. We're gonna write if the angle is greater than 0.1, we're gonna remove prim by the geometry itself and the prim number and the variable 1. Okay. If you want to know more about this, go and read about geoself and primnums. But this will basically remove any primitive that has the attribute that is greater than 0.1. Make sure to run this over primitives because those are the ones we want to remove. And if we now go ahead and simulate this, let's just make sure that we have spring. We have the first input to the spring here selected. Let's run this simulation and see what happens now. We can see that they actually break here in two parts. And they break even a little bit more here. So the main areas where the bend is big, which is here, the impact point, and down here, where it kind of bends from the inactive group. Or the, yeah. And we can even see that there's really nice features when it lands on the ground. It kind of bends as well here, which looks really cool. But yeah. And this is a very nice, like, very physically accurate way of things bending. I can think of a lot of things that bend before they break, like rubber, plastic, wood would probably bend a little bit before it breaks, before it shatters. Some softer, like stone, probably. Yeah, maybe mud would break like this. You can think of a million things that can break like this. First bending and then breaking. And this is kind of what we have achieved here. But we can also go ahead and define this to be a smaller angle. Let's do 0.05. And now if we go ahead and resimulate this, it's going to break in way more areas. Hopefully. It should. Yeah, here we go. As you can see, it still flexes, it still bends, but it's not allowed to bend as much, you know? And we can definitely play around with this even more. We knew that the biggest number was 33. Let's put a 25, 0.25, and see if it actually breaks anywhere. Almost. Yeah, there it breaks. As you can see, it was really rough breaking, but it's still, at the end it did break. So it very flexes a lot, and then poof, it breaks off. So you can get a lot of cool looks with this. I would definitely encourage you guys to go ahead and go over this yourself, and go over all of this, and take a look at the notes I've wrote, and play around with the number of like angle to break it on. But yeah, this is it for breaking spring constraints and getting a nice bend into your simulation. So that's it for this tutorial, and I'll see you guys in the next one. Thank you.